Good morning. Today, inshallah, we are going to talk about nucleus and elementary particles. I want you to open your student book, page 138. Now, open your student book, page 138. Today, inshallah, we are going to talk about what's meant by nuclear components and what's meant by nuclear chemistry. At the beginning, to study nuclear chemistry, we must know that the nucleus consists of many different particles, like protons and like neutrons. These are the main components of the nucleus. And the nucleus, as you know, is the central part of the atom. The central part of the atom is called nucleus. So, now, Rutherford was a scientist who discovered that the atom of any element contains a central part called nucleus. And Rutherford constructed a model to describe the atom. He reached that the atom contains a heavy particle inside the nucleus. These heavy particles are called protons. Protons are positively charged particles. The number of protons is called atomic number. So one of the important things to know in nuclear chemistry, that atomic number, its symbol is Z, means the number of protons. The number of protons. And you studied before that the number of protons equals the number of electrons. Number of protons equals the number of electrons. And here we have a give reason question. Give reason. Atom is electrically neutral because the number of protons equals the number of electrons. Okay, so the atomic number is symbolized by Z. Each atom has its atomic number, and also it has another number which is called mass number. Mass number symbol is A. Mass number means number of protons plus number of neutrons. So each atom has A and has Z. And also we have the number of neutrons, N. How can we calculate N? N equals A minus Z. So mass number minus atomic number give us the number of neutrons. So these are the main things for the symbol of an atom during nuclear chemistry. We will use this symbol in all nuclear chemistry. This symbol is XAZN, where X is the symbol of the element, Z is the atomic number, A means mass number, where N is the number of neutrons. We will use this symbol in all our study in chapter 5. So this symbol is too important. Now, for example, if we have aluminum 13 and the mass number is 27, the question is, what is the number of neutrons in aluminum? To calculate the number of neutrons, we use the rule N equal A minus Z. So where is the A? This is the A. 27. Where is Z? This is Z. 13. So 27 minus 13 give us 14. So we have 14 neutrons in aluminum normal isotope, which is aluminum 27. Okay, here the number of neutrons is 14. And like this, many questions will be like this in different cases. So, like carbon 12, carbon 14, carbon 13. any different atom can be given to you, and you will calculate the number of neutrons according to this rule. And you can know the number of protons from the atomic number. This is the atomic number, which means protons number. Okay? And the number above will be the mass number. Okay. Now, let's move to the other point. As you know from the previous years, that around the nucleus there are many energy levels, which are 7 in the heaviest atom. According to what Bohr said, Bohr made a model. In this model, the places in which electrons revolve are described as energy levels. So we have a certain number of energy levels. These are the places in which electrons revolve. And according to what Rutherford said, atom contains a central particle which is called nucleus. This central part, which is called nucleus, in which all the mass of the atom, or the most of the mass of the atom, is concentrated in its nucleus. So we have a give reason question here. Give reason. Mass of the atom is concentrated in its nucleus. Why most of the mass of the atom is concentrated in its nucleus? The answer is because the nucleus contains two heavy particles, which are protons and neutrons. So most of the atomic mass is inside the nucleus. And as you know, electrons are two small particles, are very tiny particles. So the mass of electrons are neglected. We can't consider the mass of electrons. So most of the atomic mass is concentrated in its nucleus. Okay, this is the first part of the lesson. Now, we have different atoms for the same element that contains different mass numbers. These are called isotopes. In all nuclear chemistry, we will use the term isotopes. What we mean by isotopes? Isotopes are atoms of the same element that have the same atomic number, Z. They have the same atomic number, which is Z. But they have different number of neutrons. They have different number of neutrons, but the same number of protons. Okay? This is called isotopes. So, for example, hydrogen has different isotopes. The first isotope is H11. This is called protium. Okay, this is protium. The second isotope is H21. This is called deuterium. The third isotope is H31. This is called tritium. Okay, these are the different isotopes for hydrogen: protium, deuterium, and tritium. The nucleus of protium is called proton. Proton has one proton only. This is the shape of proton. It's one proton only. Okay? While deuteron, at the end we have On. This is the nucleus of deuterium atom. So deuterium is the full atom, while deuterium is the nucleus of deuterium. It contains one neutron and one proton. One neutron and one proton. So its mass number is 2. As you know, mass number is the summation of proton and the neutron. So here we have 2. So the mass number is 2. Okay? The third case is tritium. Tritium is the third isotope for hydrogen. It has 3 different particles inside its nucleus. 2 neutrons and 1 proton. 2 neutrons and 1 proton. Okay? So its atomic number is 1 also, like deuterium and protium, but its mass number is 3. So we have different shapes for the same element but they have different mass numbers. Here 1, here 2, here is 3, and they have the same atomic number. In all cases is 1. So hydrogen atomic number is 1, while different isotopes have different mass numbers. Okay? Now, how can we calculate the atomic mass? Atomic mass can be calculated by knowing the different isotopes and their percentages in the nature. For example, we have copper 63 and we have copper 65. Look at your books, page 140, to understand this example. Copper 63 and copper 65 are two different isotopes for copper. Okay? How can we calculate the average atomic mass of copper? This is the atomic mass that will be written in the periodic table. What we will write above copper in the periodic table? Which number? 63 or 65 or what? To know, we must calculate the average atomic mass. How can we calculate it? The solution. We must calculate the contribution of copper 63 in the atomic mass, and we must calculate contribution of copper 65 in the atomic mass. Then we will add the two contributions together. This will be the average atomic mass of copper. So for example, contribution of copper 63 can be calculated by multiplying its percentage times its atomic mass. So for example, its atomic mass is 62.9. We will multiply this with its percentage. Its percentage in nature is given here, 69.009%. So we will write 69 divided 100. This is the percentage of this copper. Then multiplying this percentage with the atomic mass of this copper, we will get 43.47 AMU, atomic mass units. Now, let's calculate contribution of the other type of copper, which is copper 65. Contribution of copper 65, we will multiply also its percentage times its atomic mass. Its atomic mass will be 64.9. So write it in your book, 64.9. Okay, 64.9, this is the atomic mass of this copper. Multiplying this atomic mass to its percentage, we will get 20.069 AMU. Now, adding these two numbers, adding these two contributions, we will have the atomic mass of copper. This will be written in the periodic table. So in the periodic table we write copper 63.55 AMU. This is the average atomic mass of copper, and this will be written in the periodic table. And also we can express the two contributions and the two percentages by a diagram like this. We can write like this. We have about 30% of this isotope, copper 65, and we have about 70%, nearly 70% of this isotope, copper 63. So we must understand these diagrams also. The question may come as a diagram. We may find different questions like diagrams. Okay, so we must understand what do these diagrams mean. Here, this is the percentage of the first isotope, and this is the percentage of the second isotope. Okay, in another case, what can you do if the question give you one percentage only? If the question give you that copper 65 is 30%, can you conclude the other isotope percentage? Yes. What will you do? 100 minus the number given. 100 minus the number given. This will give you the percentage of the other isotope. So this is also another idea that can be given. Okay? Now, I hope you understand. Let's move to the second point. We have different terms like isobars and isotones. These are different than isotopes. Isobars are the nuclei of atoms of different elements that have the same number of mass, the same mass number, the same A, but they are different in the atomic number. For example, F17-9 and O17-8. They have different atomic numbers, but they have the same mass number. This is called isobars. Also, we have something called isotones. What are isotones? Isotones have the same number of neutrons. This is the same number of neutrons, but they have different mass numbers and they have different atomic numbers. These are called isotones. So isotones have similar number of neutrons. Isobars have similar mass numbers. While isotopes, this is the main of our study, have the same atomic number, but they are different in mass number and number of neutrons. So what's the difference between tritium, deuterium, and protium? Can you say the difference? Okay, the difference is the number of neutrons, and according the mass number. I hope you understand this point. Now, what about mass and energy units? Now, as you know, Albert Einstein was a great physicist and a great chemist who put this rule: E equal mc square. E is the energy calculated by joules. M is the mass calculated by kilograms. C is the speed of light, and it's a constant value, which is 3 times 10 power 8 meter per second. Yani means 300 millions meter in each second. This is the speed of light, and as you know, it's a constant. Okay? Albert Einstein proposed that if you multiply any mass with the speed of light square, this mass will change into energy. So if you are going to calculate this amount of energy, you must multiply the mass times the speed of light square. Okay, for example, can we calculate the energy resulted by conversion of one atomic mass unit into energy? Okay, if we said that atomic mass unit means 1.66 times 10 power minus 27 kilograms. This is one atomic mass unit. I want to convert it into energy. What can I do? According to Einstein, this mass must be multiplied with 3 times 10 power 8 all power 2. So we will get 14.9 times 10 power minus 11 joules. This is the amount of energy resulted by conversion of one AMU into energy. Okay? Now, this amount of energy is too important. Okay? This is the energy resulted by conversion of one AMU. We have a small unit that we can use in nuclear chemistry and in nuclear physics also. This unit is called 1 electron volt. Electron volt means the energy resulted by moving the electron for a certain distance. This energy equals 1.6 times 10 power minus 19 joules. This is the value of 1 electron volt, 1.6 times 10 to the power of minus 19 joules. So mega electron volt or million electron volt means multiply this number with 10 power 6. So the power of minus 19 will be minus 13. So this is 1 mega electron volt. MeV. MeV means mega electron volt or million electron volt. It equals 1.6 times 10 to the power of minus 13 joules. Okay? Now, if we take this value and divide this number on this value, what we will get? If you divide this energy by joule on this number by joule, we will get 931 mega electron volt. This means that 1 AMU is equivalent to an amount of energy equal 931 mega electron volt. So 1 AMU give you energy 931 mega electron volt. Okay, so we can use this amount to obtain a rule. E by mega electron volt equals mass by AMU times 931. So we will call this the second rule. So we have the first rule and we have the second rule. We will use this rule to get the energy in joules, and in this rule the mass is by kilograms, and we will use this rule to get the energy by mega electron volt, and here the mass is AMU. Okay? Don't forget that if the mass is 5 grams, how can we get it by AMU? We know that 1 AMU equals 1.66 times 10 power minus 24 grams. So 5 grams can be put here. 5 grams give us how many AMU? To know this value, we must use cross multiplication. So 1 times 5 divided 1.66 times 10 power minus 24, and we put this value in a bracket to get the x. So x will be equal the number in AMU. So you can use this relation to convert. You can use this relation to convert any value between gram and AMU. 1 AMU equal 1.66 times 10 power minus 24 grams. And also we have 1 AMU equals 1.66, the same number, times 10 power, but we will change the power only. Instead of power minus 24, it will be minus 27 if you are going to convert to kilograms. You will use this relation to convert the mass between AMU and kilogram. And you use this relation to convert 1 AMU to grams. Or if the number is given by grams, you can return it to AMU, and vice versa. You can use this conversion way for gram and this conversion way for kilogram. Okay?